I just started recording actually because I forgot. We'll do the limit as x approaches -2 overall. And we'll find, oops, not f. We'll find g of -2. Okay, so I want you guys to find those four. Okay, who can let us know what we got for the first one here?
3.
Cool. All right, Brendan, what did you get for the second one as we approach -2 from the right?
3.
3, good. All right, Stash, what did you get as we approach -2 and our overall limit?
3.
3, nice. Okay, so we can see here that as we approach x equals -2 from the left and from the right, we're approaching the same y value. Remember, limits are y values. Because our one-sided limits are both the same number, our overall limit is that number. And let's see. Dylan, what did you get for g of -2?
Is that undefined?
Nice. It is undefined. Great. So we do not have any y value for when x is -2. It's an open dot and there's no closed dot anywhere. So it's undefined. Great. So we're not continuous there, we're discontinuous. Who remembers that type of discontinuity?
Like in
whole.
Removable.
Yeah, it's a whole, it's called a removable discontinuity. Nice job, guys. Cool. Okay, that is the review of the graphical limits. Because I recorded a little bit late, I'm just gonna go back to this first page real quick. This is our topic for today. Cool, we're gonna do limits graphically and algebraically. We did limits graphically. Okay, so that was our review of limits graphically. Let's move on to algebraically, where we don't have a graph necessarily. We only have the function written out. And this is gonna be a new idea for you guys. So this is gonna be evaluating limits algebraically. If you are like ever confused on something like this, your calculator is a very handy tool for when you're just doing something algebraically. And so you can always just use your calculator and plug into your calculator. Okay, so let's do a couple examples. We want to find the limit as x goes to 2 of x cubed minus 4x squared plus 1. And off to the side, I'm going to sort of write some steps that you want to think about when evaluating a limit. So this one's clearly algebraic, right? There's nothing graphed. So this one's more like mathy. You have to write stuff down. All right, your first step always with stuff like this is to use what's called direct substitution. Does anyone want to guess what that means in this case?
It swaps something.
Can you explain what you mean by that?
Like it was you could like substitute the x for something else, maybe. I don't know.
Okay, what do you think we want to plug in for x here?
2.
Yeah. Cool. So we can see, right, if we plug this function into our calculator, it's just a cubic function. It's going to look like a roller coaster kind of. And it's going to have like 2 turns in it. And there's not going to be any holes or gaps or jumps or anything that would make it a discontinuity. The reason we know that is because there's no like denominator that could be 0, nothing weird. So basically our limit as we approach 2, we just plug in 2. So let's plug in 2. So I'm going to plug 2 in here and here. So I'm literally going to just directly substitute 2 in for x. So I'm going to have 2 cubed minus 4 times 2 squared, PEMDAS, right, plus 1. So this will give us 8 minus, we square first, right? So that's 4 times 4, so that's 16. So we'll have negative 8 plus 1, so this is negative 7. So when you use direct substitution, sometimes you can just get your answer. That's the answer to the limit. So if we use direct substitution, if we get a value, that is the answer. And then you're done. That one's pretty nice. That means the coordinate point on this function was 2, negative 7. And so there were no like weird things with that function. It was just the limit. Our graph just went to that value on both sides and we were good. Okay, let's try another one. Let's do the limit as x goes to pi over 3. Of the cosine of x over the sine of 2x. This is one that you're able to also just, you obviously, you know, you want to first do direct substitution. So that means literally plugging in the x value for our function. So when we plug that in, we'll have the cosine of pi over 3 in our numerator. And then we'll have the sine of 2 times pi over 3, which is 2 pi over 3 in our denominator. So you guys can write in what those values are, use your unit circle or just think about it. And then we'll simplify and get our answer. Okay. The cosine of pi over 3, who has what that is there?
1/2.
1/2. How about the sine of 2 pi over 3?
Root 3/3 2.
Cool. Okay, our 2's can cancel. So we have 1 over root 3, which when we rationalize will give us root 3 over 3. Okay, so we got just a numerical value again. That is our answer to our limit. Okay, the next thing, and I don't have an example for this one. I'm not really including it, but I'm going to just write it on here. If you get undefined, And what does undefined mean in math as a fraction? It means that we have a non-zero number over 0. So if we get undefined, if you got like, 7 over 0, that would mean it's undefined. That means the limit does not exist. So I don't have an example of that kind, I don't think, and that one's not going to be on your assignment. But we'll get into factoring here next, actually. All right, so the very last thing is if you get what's called indeterminate form, INDETERMINATE. Indeterminate form is 0 over 0. That does not mean undefined. It's called indeterminate form. Undefined is if you had like 4 over 0. Indeterminate form is literally 0 over 0. So if you get that, then you should try an algebraic method. And the one that we're going to look at this year, you'll have a few more next year in AP, but we'll try factoring. We'll try factoring and canceling. This is a common way to get around a removable discontinuity. So we have to dig deep in our factoring brains here, which we've done this a little bit this year. So let's take a look at this next example. We're going to have the limit as x approaches 3 of x squared minus 9 in the numerator over x squared plus 2x minus 15. So as always, our first step is direct substitution. So what I want you guys to do is use direct substitution and plug in 3. See what happens. Okay, so when we plug in 3 in our numerator, we get 9 minus 9. And in our denominator, you should also get 0, because we'll get 9 plus 6, 15 minus 15. So we get what's called indeterminate form. Indeterminate form means that the limits still exist. You have to use an algebraic method. And again, there's one of the more common ones is factoring. And so we can see that both the numerator and the denominator here are factorable, right? Does anyone remember how we can factor this numerator here?
X plus 3, x minus 3.
Great. And what is that called? Someone else. Who remembers what the numerator is called mathematically?
Difference
come
of
on,
two
guys.
squares.
Yes, difference of squares. Thank you, Kobe. Awesome. Okay. So this numerator is a difference of squares, right? This is a perfect square, and we're taking a difference, literally. So we take the square root of x squared, put it first, the square root of 9, put it second, and 1 plus 1 minus. Okay, so we've factored the numerator. Our denominator is a quadratic trinomial where a is 1. So we need two numbers that multiply to negative 15 that add to 2. So how is our denominator going to factor? Hmm.
5 and -3.
Nice. So x plus 5, x minus 3. Okay. So if you were to FOIL either one of these out, right, we get back to the respective numerator or denominator. All right, so we factored. Now we can see what happens, right? We can cancel now because we have factors that are being multiplied. So this is legal canceling. The x minus 3's can cancel out. If you notice, that is what gave us the issue, right? If we were to plug in 3 here or here, it made it 0. That was the original issue. Factoring and canceling removed that issue. Now we can plug in 3. Now we can redirect substitute. What this is doing graphically is there's actually a hole in this graph at x is 3. It's a removable discontinuity. That means the limit still exists, there's just a hole there. So we're finding what that limit is by this algebraic method of factoring and canceling. So now we can direct substitute. So I'm going to call it let's redirect substitute. So we can plug in 3 now. So we'll have, so I'm going to plug in 3 here and here. So I'm going to have 3 plus 3 in the numerator and 3 plus 5 in the denominator. No more issues with zeros because we eliminated it. So we have 6/8 or 3/4. Cool. That's our limit. So indeterminate form, again, is 0 over 0. If you get that, you have to use an algebraic method to find the limit. One of the more common algebraic methods is factoring, which is the one we're going to focus on this school year. In AP Calc, you'll also get rationalizing and stuff with trig that we're not focusing on this year. So for you, you just got to factor and cancel, then re-plug in the number. You should be able to eliminate the issue through factoring. Cool. All right, let's do another one. These are fun. Let's try. That was example 5, I think. So here's example 6. The limit as x goes to -4 of x plus 4 in the numerator over x cubed minus 16x. First step, direct substitution. See if you get an answer outright or if we get indeterminate form. Okay, when we plug in -4, we'll get 0 in the numerator. And then when we cube -4, we get -64, right? And then this is minus a -64 or plus 64. Just wanted to write that out because that got a little tricky. So we do end up getting 0 over 0. 0 over 0, again, is not undefined. 0 over 0 is in mathematics what we call indeterminate form. The limit still exists, so we're going to factor. So in order to factor, we look at the numerator. The numerator can't be factored at all. There's no GCF or anything there. But ideas on what we can do in the denominator. What a good first step is.
Factor out the x.
Nice. Factor out your greatest common factor. In this case, both terms have an x in it. Okay, then we're left with, if we take an x out, we're left with x squared and then a minus 16. All right, this still doesn't eliminate the issue. We have to keep factoring. So in our denominator, this is a difference of squares that we saw in the last problem. Perfect square minus another perfect square. Go ahead and factor those, or that rather. All right, we should end up getting x plus 4 and x minus 4. Okay, this in the numerator right here is technically a factor. I mean, it's the only thing up there. So if you want to put in parentheses, you can. Canceling will eliminate our issue, right? If we were to plug in -4, this gives us an issue because it gives us 0, and this factor gives us an issue because it gives us 0 when we plug in -4. They cancel. So let's look at what we're left with. We're left with the limit as x approaches -4. This numerator still exists. Anything divided by itself cancels out to 1. So we have a 1 in our numerator still. Don't forget that. Our denominator contains an x and an x minus 4. I'm rewriting this one as opposed to not rewriting the last example because this one's a little more complex. We wiped out one part of the fraction. That doesn't mean that part of the fraction is gone. It means that it's 1.
Mom?
No, I'm not your mom.
Oh, sorry, my bad.
I like kind of badly want like a funny viral thing to happen. That would be so great. I've been enjoying watching this. Okay, we can directly substitute. So I want you guys to practice. I want you guys to practice. Direct substituting in -4. Direct substitute. So now you can plug in x is -4. And that should give us our answer. All right, I ran out of room to write my steps, so I did it in my head. This is -8. -4 times -8 is +32. PEMDAS never goes away, so be careful that you're doing order of operations correctly. You could also, I guess, distribute through. That's more complicated than it needs to be. So our limit is 1/32. Okay, I have one more example for you guys, and then we're done for today. The limit as x goes to 0 of 5x to the 4th plus 8x squared over 3x to the 4th minus 16x squared. So if we direct substitute 0 in, this one's pretty easy to see that we'll get 0 since all our terms will turn to 0. So our first step is realizing we get indeterminate form. Therefore, we have to employ an algebraic method, in this case, factoring. Our first step for factoring always is GCF, which we have. So the GCF in our numerator is x squared. We can't take a number out because 5 and 8 don't have a GCF other than 1. So I want you guys to write what's left when we take out an x squared. And then you can do the same thing in the denominator. Okay, who would like to share what they got in the numerator here?
Five x squared plus 8x.
Thank you, just plus 8.
Oops, yeah, you're right.
Awesome, thank you, Charlie. Okay, how about in our denominator? How can we factor that?
3x squared minus 16. X squared on the outside.
Awesome. Thanks, Daniel. Okay, now the x squareds can cancel out because they're factors. And then we can direct substitute in 1, or 0, sorry. We can direct substitute in 0. So when we do that, we'll have 0 plus 8 in the numerator, right? I don't need to write all that. Obviously, multiplying by 0, this will turn to 0. And then in the denominator, we'll have 0 minus 16. Cool. And so that will give us 8 over negative 16, which we want to write the negative either in the numerator or out in front, so negative half. Okay. That is it for your notes today. I'm going to email out your assignment. It'll be due Thursday at by 3:15 p.m. and then spring break. All right. Wednesday's class is going to be kind of just like a limits practice day, so it won't be the whole time probably. But yeah, so I also found out it's just my class that needs the password in case I didn't say that already. So you don't have to worry about that in other classes. Good times today with all this. Any questions, guys? Okay, have a wonderful day. I'll see you on Wednesday.
You too.
Thanks.
Thank you.
Mr.
Sorry
Mod,
about that.
I have a question.
Sure, what's up?